Question number 1. This is about how to use Maxwell-Boltzmann distribution. To write the expression for Maxwell-Boltzmann distribution, you just copy this equation, and this equation is about the fraction, F means fraction, of molecules has a certain speed. For example, what is the fraction or percent of molecules in a collection of molecules that has a speed 40 meter per second? Okay, what's the percent? So to calculate, you just plug in 40 here and use the mass of the molecule, the temperature, and you can calculate what is the fraction of molecules that has a certain speed. Now, express the fraction of molecules that have speed in the range v to v plus delta v. For example, delta v is 0.7. So we are calculating the fraction of molecules have speed between 40 meter per second to 40.7. So in this range. Okay, what is the percent of molecules? So if we look at the diagram here, let's say this is 40 meter per second. So we are now calculating a small range, 40 to 40.7. If this range is very small, like here is 0.7, okay, difference, then in calculus we can just use 1 point, okay, the fraction of 1 point times the range, tiny range. But if the range is measurable, okay, so here from V1 to V2, then you separate into many segments, you add together in calculus, that's the integration. So integration of fraction of molecules times the tiny range, integration from V1 to V2. Okay, we've seen this in our lecture notes already. So that's the fraction in a measurable range. So next, calculate the fraction molecules that have speed in the range 292 to 298. Okay, now 292 to 298, the range here is 6 meter per second. All right, and the speed itself is 292 or 298. So the range is a small range, and therefore we can simplify, just use this equation. So we can use one of the fraction inside the range times the range delta v. Okay, the fraction of molecules of a speed in this range. So which speed we can use? Usually you choose the center. All right, so 292, 298. The center is 294 or 5. So 5. Yes. So the speed, all right, in this range, the center is 295. So you calculate the fraction here or this one. Okay. All right. The speed is 295. Calculate the fraction of molecule 295, and then times the range 6. Okay. Now to calculate this one, there are ways. You just plug in all the data, but here, just for simplicity, we replace m divided by 2 pi kt. Now pi k times Avogadro's number give you r, 2rt, and m times Avogadro's number is mass, molar mass. So this equation can be written as m divided by 2rt. Let this to be a, then the Maxwell distribution becomes 2 pi a divided by pi v squared e to the negative a. So this can also simplify. Now you don't need to do this step. You just plug in every data, calculate. So you plug in the speed as 295, you calculate Maxwell-Boltzmann distribution. But here, for simplicity, we calculate a first. All right, you calculate a, m is the molar mass, 2r temperature. You calculate a, and then plug in the speed 295. Okay, so the speed is 295. A already calculated. All right, so this is A. Okay, and then plug in the answer is 9.606 times 10 to the minus 4. This is the fraction of molecules has speed 295. That's the center of the range. And then you times the range is 6. Okay, so that gives you fraction of molecules in this small range. Okay, so that's question number 1. Question number 2. Determine the average speed and average kinetic energy of oxygen and carbon tetrachloride at 298 Kelvin. So to calculate the average speed, so all you need to do is go to lecture notes, find this equation. Average speed is square root 8 RT over pi m. Okay, so for oxygen, the mass, molar mass, all right, remember if you look at the periodic table, oxygen is 16 gram per mole, but you need to times 2, so that gives you 32 gram per mole. Now in SI unit, gram should be kilogram, so you times 10 to the minus 3, all right, and temperature 298 Kelvin, square root, you get 444 meter per second. So that's the average speed for oxygen. For carbon tetrachloride, the molar mass, you can use carbon is 12, chlorine is 35.5 times 4, so you get 54 times 10 to the minus 3, and that gives you speed 203. And you can see in average carbon tetrachloride is moves slower than oxygen because it's heavier. Okay, next calculate average kinetic energy. Now there are 2 ways to calculate average kinetic energy. Method 1, if you remember our conclusion that for all gases, the average kinetic energy equals to 3 over 2 kT. Okay, that's an important equation and tells you that temperature is a measure of average kinetic energy. All gases has the same kinetic energy if temperature is the same. And so whether it's oxygen or carbon tetrachloride, you already know they have the same kinetic energy at 298 Kelvin. So half K Boltzmann constant temperature, that gives you average kinetic energy. Now in method 2, you can calculate each of them using the average mean square speed. So remember, for a collection of molecules, the average kinetic energy is calculated by half m v square average. So this is the mean square speed. And in statistics, we square root it called root mean square speed, and then you have to square it so that you get average mean square speed. So calculate root mean square speed using this equation for oxygen, for carbon tetrachloride, and then you square it. All right, so here is oxygen and here is carbon tetrachloride. You get the same value here. They are all the same. Okay, note that when you calculate kinetic energy, you use root mean square speed. So mean square speed means you V1 square plus V2 square add all together divided by total number of molecules. So that's the mean square speed. You don't use this average speed. Average speed is V1 plus V2 add together divided by n. Okay, so if you use this one and then you square it, you calculate kinetic energy. That's not correct. You should use the average square v squared, and so that's the mean square speed to calculate the kinetic energy. Question number 3. how many collisions does a single argon atom make in 1 second? So this is about collision frequency, okay, collisions in every second. And you can easily find the equation from lecture notes. Collision frequency is calculated by cross-section area, relative speed, number density. And the relative speed is square root 2 times average speed. And the number density is the pressure divided by kT. So here is the equation. Square root 2 cross-section area, in this case, for argon is 0.36. All right, and the average speed we're going to calculate first, and the temperature is 25 Celsius. You need to change to Kelvin, and the pressure is 10 or 1 or 10 to the minus 5. So first calculate average speed for argon at 25 Celsius, so 298 Kelvin, and the molar mass for argon 40 times 10 to the minus 3, and that gives you average speed for argon is 397.2 meter per second. All right, so plug in this into here. Okay, so for pressure 10 atmosphere, all right, so here is 10, and you times 1.03 times 10 to the 5th power to change to Pascal. So 10 atmosphere change to Pascal, and change everything to SI unit. For example, nanometer squared, you need to times 10 to the minus 9 squared. So that's 10 to the minus 18. So the answer will be 5 times 10 to the 10th power per second. Every second, argon will make 10 to the 10th power collisions. If you reduce pressure, all right, according to this equation, all right, when you reduce pressure, you expect collision frequency will also reduce. All right, and so plug in the pressure 1, then the answer is 5 times 10 to the 9th power. So pressure reduced 10 times, collision frequency reduced 10 times. Similarly, if pressure becomes 10 to the minus 5, then the collision frequency becomes only 5,000 per second. So very fewer collision frequencies at lower pressure. Okay, the collision frequency is small at low pressure. Question number 4. Calculate the mean free path of molecule in air using this cross-section area at 25 degrees. All right, 10 atmosphere, 1 atmosphere, 1 microatmosphere. So again, you can easily find equation for mean free path, which is 1 over square root of 2 cross-section area number density, and number density is pressure divided by kT. So this you get this equation, kT over square root of 2 cross-section area and the pressure. So for 10 atmosphere, this is how we calculate mean free path. Boltzmann constant, temperature, and square root of 2 cross-section area again goes to a meter squared, and the pressure you need to change Pascal. So here is about 6.7 nanometer. So every the molecule can travel 6.7 nanometer before it make a collision. All right, and so 10 atmosphere you expect lots of collisions. So you can only travel very short distance. When you reduce pressure to 1 atmosphere, using this equation, the mean free path becomes 67 nanometer. And in 1 microatmosphere, the mean free path becomes very long, 6.7 centimeter. In other words, the molecule can travel 6.7 centimeter before it make a collision at this low pressure. So at a low pressure, mean free path is extremely large, and mean free path is a measure of the intermolecular distance. So the distance is much larger than the size. The size is negligible. So it's just like dots moving. So and also molecules they don't attract each other, they don't repel each other, they only make short collisions that is elastic, kinetic energy is conserved. So again, it justifies it's an ideal gas at a very low pressure. Question number 5. Because the mean free path is inversely proportional to the pressure, like in this equation, and so if you reduce the pressure, you can increase the mean free path. And one way to do it is use the vacuum technique to lower the pressure, increase the mean free path. Now suppose there's a cubic vessel of size 1 liter filled with argon gas at 25 degrees. What pressure do you need to achieve a mean free path comparable to the size of container? So first calculate the dimension of this container. 1 liter means the length is 1 decimeter or 0.1 meter. That's the dimension of this container. And so for the mean free path to be comparable, that means the mean free path is 0.1, and we want to calculate the pressure. So modify this equation, the pressure can be calculated by kT divided by square root 2 cross-section area mean free path. In this case, is 0.1. Okay, so plug in all the data. Boltzmann constant, temperature, square root of 2, cross-section area, mean free path, give you 0.081 Pascal. And that can be converted to torr, is 6.1 times 10 to the minus 4. And this pressure can be achieved by a regular mechanical pump. Using regular mechanical pump, and you can lower pressure to 6.1 times 10 to the minus 4. And in that case, the mean free path for argon can be 0.1 meter, the dimension of a container.